Okay, so we are going to look at solving Laplace's equation on a rectangle. Now, there are only so solving Laplace's equation on the rectangle. What is going to eventually come down to is we're just going to solve Laplace's equation 4 different times, and each time we're going to solve it is going to be like the one that we're about to look at. In general, solving Laplace's equation on a domain is not easy. Doing it generically for a generic domain is really difficult, and it's not something that we're going to look at in this class. So we're going to solve the following problem. We're going to have the Laplacian of u is equal to 0, and we're going to say that u of x0 is equal to 0. We're going to say u of xb is equal to some given function f of x. In the notes it says x. We're going to have u of 0y is equal to 0, and u of ay is also equal to 0. So if you look at this as a diagram, what's going on here? Well, we have a rectangle. The x goes from 0 to a, and the y goes from 0 to b, so something like this. Let me grab my eraser and make that look a little bit nicer, or a little bit bigger, I should say. This is a, this is b. Sorry that the camera is a little tilted. I couldn't figure out how to get it. Anyways, so a and b. And what do we know? We know that along this line, when y is equal to 0, we know that here u is equal to 0. Okay, along this line, x is equal to 0, and then y is varying. Right here we know u is equal to 0. And then this is wrong here. This should say u of ay is equal to 0. And so we know along here u is equal to 0. Okay, and then along the boundary up here, we know u is equal to f of x up here, when y is equal to b. Okay, so here's how we're going to solve this. We're going to use separation of variables. And notice that as we go in the x direction, like as I go from here to here, if I think about the x problem, looking ahead to how we're going to do separation of variables, if I think about the x problem, I'm always going to be equal to 0 here and equal to 0 here. So that's going to give me like a boundary value problem in the x variable. Now the y variable will be a little bit different. I'm going to still get a second order equation in the y variable, because I'm going to remember this includes a second derivative in the y variable and a second derivative in the x variable. I'm going to get a boundary value problem here, but I'm also going to get a second order ODE in the y variable. But I'm going to need two conditions because I'm going to have two different unknown coefficients. And the two conditions that I'm going to get, the two conditions that I have, I know what u is equal to here, and I know what u is equal to here. And that's what's going to let me solve for the unknown coefficients in the y problem. Okay, so without further ado, let's just get into this. As we've been doing, we're going to assume that we can write our function u of xy as a function of y times a function of x. And again, since I know my x boundary values, I know that for any y value, if x is equal to 0, the function is equal to 0. And for any y value, if x is equal to a, the function is equal to 0. It means the phi of x thing, this should be my boundary value problem. I have a boundary value problem for phi. I do not have a boundary value problem for h. In a certain sense, I do, but I have a homogeneous boundary value problem for phi because I know it's equal to 0 here and 0 here. In principle, we could do it the other way, but my boundary value problem for h would not be a homogeneous boundary value problem. Okay, so let's look at solving this. So as before, this is my function. I'm going to plug it into the PDE. So I'm going to get the x derivative, or let's say the x derivative, man. So if I do the x derivative, the double x derivative, that's what I get, plus the double y derivative, that's equal to 0. Rearranging, so notice what's going to happen when I rearrange. I'm actually going to get minus h double prime of y over h of y equals phi double prime of y, x over phi of x. Okay, remember with the wave equation, the wave equation was utt equals utt equals uxx. So there was a minus sign there, so we didn't have the minus sign there. But if you do the algebra, you either have to have a minus sign there or a minus sign there. We're going to say this is equal to minus lambda to make everything look like it did before, so therefore we put the minus sign there. So for the x problem, we'll have phi double prime over phi equals minus lambda. So it's phi double prime equals minus lambda phi. And the boundary values tell us that phi of 0, okay, let's be careful, it's not phi of pi anymore, it's a more generic value, phi of a is equal to 0. Okay, so this is a second order differential equation. A similar argument shows that lambda has to be a similar argument to what we did in previous lectures. Show that lambda has to be a positive real number. And so the general solution to this is going to be phi of x is equal to a cosine square root of lambda x plus b sine square root of lambda x. And now we're going to use our boundary values. The boundary value at 0 still tells us that this is going to be equal to 0 by the boundary value at 0. You plug in 0 here, you get 0 on the left-hand side, and on the right-hand side, that term is 0, this factor is 0, so you're just left with a, so therefore a is equal to 0. Okay, now for the boundary condition at a, it's going to be a little trickier. We're going to have 0 is equal to phi of a, and this is equal to b sine square root of lambda a. Okay, well b is not equal to 0, because if b was equal to 0, then phi would be identically equal to 0, and we don't care about the trivial solution. So therefore, for this to be equal to 0, we need to have the square root of lambda times a needs to be equal to some integer multiple of pi. Okay, the only way that you can get sine of something to be equal to 0 is if that something is equal to an integer multiple of pi. And so now what this tells us is that the kth eigenvalue, lambda k, is going to be the square of k pi over a. So it'll be k pi over a squared, just like this. Okay, so that's the eigenvalues, and then the eigenfunctions, phi k of x, will just be equal to, I'll forget about writing the constant, will be sine. Any non-zero multiple of this will give us an eigenfunction, sine of k pi x over a. Okay, so now I'm going to erase some stuff so that we can solve the h problem. So lambda k, I'll just record our information. Maybe I'll record our information over here just so we can come back to it. Lambda k is equal to k pi over a squared, and then the eigenfunctions phi k of x are sine k pi over a x. Alright, so now we're going to look at the h equation, except up here, I'm going to just replace this with what we know it to be, which is k pi over a squared. So I have minus h double prime over here. So if I just look at the h equation, so let me get rid of this. If I just look at the h equation, I can erase these minus signs. And so what this tells me is h double prime is equal to k pi over a squared times h. And so now the general solution for this is going to be h of y, and it depends on k, so I'm going to put a k there. It depends on k in the sense that there's a k there, right? The way that the product solutions always depend on k. So this is going to be equal to ak. Okay, well now here we're going to get something different. this is a positive number. So we have h double prime equals to a positive number times h. So again, this is a second order equation. The characteristic polynomial is r squared equals some positive number. So we're going to get exponentials. That's what's going to be the general solution. So this will be ak e the k pi over a y plus bk e the k pi over a y. And the AKs and BKs are as yet undetermined, but we're going to use the condition at u is equal to 0 and the condition at u is equal to b up here to help us determine what AK and BK are. Alright, so now I'm basically going to erase this entire right side of the board. The solution is going to be a sum of the phi k times the hk's, and that's what I'm going to write. So u of xy is going to be the sum from k equals 1 to infinity ak e to the k pi over a y plus bk, I think I've written too large, e to the minus k pi over a y, maybe I'll just be barely able to squeeze it in, sine k pi over a x. Sorry, there's an unfortunate glare on the board that I can't really do anything about because, well, okay, let me try an experiment. Okay, so that doesn't work. Oh, how does this work? Is this any better? Okay, so now the camera can't even focus. All right, so no, that did not work. A little more Tom Scott magic. Okay, so now how do we determine what AK and BK are? So I'm going to first use the zero boundary condition. So I know that u of x0 is equal to 0. Actually, let me write this slightly differently. 0 is equal to u of x0. Okay, let's think about what I'm going to get when I plug in y is equal to 0 up here. So this says x is whatever it is, and y is equal to 0. So when I plug in 0 up here, this exponential is 1, that exponential is 1. So what we have is AK plus BK sine of k pi over a y, x. Okay, so now we're saying that this function here is identically equal to 0. And again, just like with a polynomial, if you have two polynomials that are equal to each other, or more specifically, if you have a polynomial that's identically equal to 0, or like its Taylor series that's identically equal to 0, the only way that can happen is if all of the coefficients are equal to 0. So I've got this sine series is identically equal to 0. Similarly, this means the only way this can happen is if AK plus BK is always equal to 0. In other words, AK, well, let me just write this. AK plus BK is equal to 0, or AK is equal to minus BK. So now we know that AK is equal to minus BK. And so I'm going to rewrite this a little bit up here, reflecting that fact. So what we're going to have up here then, and I'm going to do it in a different color so that we see what's happening here. So I have AK, and this is e to the k pi over a y minus e to the minus k pi over a y. Okay, because minus AK is equal to BK, and this says AK is equal to minus BK. And if you want, you can write this in terms of hyperbolic signs. Right, what's the only difference between this and a hyperbolic sign? Well, we should divide by 2, but that 2 can just be absorbed into the constant. If you want to do that, you can write it as a hyperbolic sign. I'm not going to do that, though. All right, so now what we want to do is we want to figure out what AK is, and we're going to use this condition along here to figure out what the AKs are. So I know f of x is going to be equal to u of xb. Okay, and so now I'm just going to plug in y is equal to b up here. And when I do that, I'm going to have the sum k equals 1 to infinity ak e, whoops, I don't know why I put that up there, e to the k pi over a b minus e to the minus k pi over a b sine k pi over ax. Okay, so now what I'm going to do is I'm going to use the orthogonality of these sine functions. So what we know is the following. If I look at the integral from 0, to a of sine k pi over a, I'll say x times sine of L pi over a x dx, this is going to be equal to 0 if L is not equal to k, and it's going to be equal to a over 2 if L is equal to k. Okay, so again, we're going to use the fact that basically we can write f of x as a sum of these sine functions. And again, why we're able to do that, we'll get to in next week. But if we're able to do that, we can compute what the AKs are, or we can compute, I guess directly, we can compute what these are using the same orthogonality stuff that we did before. And so what we're going to get is that AK times e the k pi over a b minus e to the minus k pi over a b is equal to 2 over a times the integral from 0 to a, and now I'll use, let's say, z is my dummy variable, f of z sine k pi over a z dz. And now you can solve this for AK. You just divide this over and plug in your AK up there, and that's the solution to this problem. Okay, so kind of a more complicated formula that we get. We can make things a little less complicated looking if we use like hyperbolic sine here and hyperbolic sine there, for example. That'll make things look maybe a little less complicated. At any rate, this is the solution to Laplace's equation on a rectangle, where we have 0 conditions here, and then u is equal to f of x here. In the next video, I'm going to pick a specific f of x that's different than the one in the notes to help try to explain some of this orthogonality stuff that's going on.